Right, so this is lecture number 33. Let me do a quick summary of what we have done in the last two lectures. So we were talking about the semi-implicit method. Uh, After we derived the character equations, which had a particular assumption where we neglected the neighborhood terms in our velocity correction equations 1 tilde and 2 tilde, and that resulted in 1 double prime and 2 double prime, which was substituted into the continuity equation to get the pressure correction equation, which is used to solve for the p prime values. And once you have p prime values, you can use them to get the u prime and v prime values, which can be substituted, which can be then added to the u star and v star values to get the divergence free u stars and v stars. Okay. In this case, we do not get the Pn plus 1 in one step because of that assumption that we have taken, where we neglect the neighborhood terms in u prime and v prime. Okay. Then we wrote the algorithm of simple. So let's quickly summarize the algorithm and then we'll start from there. So in simple, which is a very popular method for solving incompressible fluid flow equations, we initialize some parameters such as delta x, delta y, delta t. We have to set the initial values for the velocities and pressures as long as they satisfy continuity. Then in this case, we have linearized the flux terms, mass flux terms. So what that means is that while we are solving for the velocities at the n plus 1th time in the semi-implicit equations, the mass flux is still taken at the nth time. So we set the value of mass flux. We also have to start with some initial pressure. So we can start with Pn. That's already available. So let's start with that. And then we iterate the u star and v star equations to convergence using let's say the Gauss-Seidel method, and the pressure P star remains the same here. So this gives us predicted values of u stars and v stars, and then we have to correct them because these u stars and v stars do not satisfy continuity. So we have to correct them. So we correct them using the pressure correction equation. So once we have the p prime values, we can get the next guess for u stars, v stars and p stars. And then we continue with, we go back to step number 3, which was where we again predict the values, correct them, keep doing that until the change in, until the u primes and p primes, they become close to 0. Okay, so once P star approaches Pn plus 1, that means that we have converged one time step, and then we move to the next time step by repeating this whole process again for the next time step until we have some stopping criteria that is met. All right. So this is what we have discussed now. Are there any questions about this method? Now we'll talk about a couple of ideas in simple. So one statement that we have been making is that once we correct the values of u star and v star after the corrector step, the new u stars, v stars obtained as a result of this update that we have got in step number 6, they would satisfy continuity. Okay. So what is the basis of this statement? Because see, we have made an assumption to neglect the neighborhood terms in the correction equation. So this is here on the top. So why is it that even though we neglected these neighborhood terms, here, sir. 1 a prime and 2 a prime. So we had these neighborhood terms. No, this is star. Yeah. So 1 tilde and 2 tilde. This is these are the expressions, the exact expressions for u prime and v prime. So we neglected the neighborhood terms in these expressions, and they were used to correct the u stars and v stars, right? So why is it that even after neglecting this, the new u stars and v stars we have got, the corrected ones, they still satisfy continuity? Now they are not the correct un plus 1 and vn plus 1s, but they do satisfy continuity. Right? So this is a valid question to ask. So let's start with this discussion today. So we start with un, and we ultimately have to reach un plus 1. And what we did was we predicted a u star, and then we corrected it to reach to get a divergence free u star, and then we did this repeatedly until it converges to un plus 1. The same thing for vn plus 1 as well. So this dotted line is divergence free velocity field. So let's look for an answer for this. So let's write equation number 4, which was the equation for satisfying continuity at time n plus 1. So this was the continuity equation. That is what you get if you discretize this using the finite volume method. Right? So you have velocities at the 4 boundaries times the area, dotted with the area vector. So on the east and west faces we get the u values, and the north and south faces we get the v values. And then what we did was we substituted for the expressions for u prime and v prime on the 4 boundaries in terms of
equation
4. So we have numbered the equation earlier. You can go back and look at this equation. And then we had written, I'll just write for one of the primed velocities. So we had an expression something like this. The indices may not have this, this is the same as what we have written. I'm just writing it in a more compact form. So we had the neighborhood terms. Then we have some pressure difference, difference of P prime, and then we neglected this term and we substituted expressions like this into equation number 4 to get an equation for P prime, and we solved the equation and we got a P prime. We substituted back into this second expression and we got U prime and V prime, and then we added them to the U stars and V stars to get the divergence free, not n plus 1, divergence free velocity fields. N plus 1 is when you iterate it again and again. Okay, so let's think about it. The first equation that we have written, this is satisfying continuity. And then what I have done is I have put an expression for U prime and V prime in terms of P prime and then solve the equation to get P primes so that this equation number 4 is satisfied. Even though I made an assumption by neglecting some terms in the second expression, but whatever U prime I have got from the second expression is ensuring that the first equation is satisfied. So if the first equation is satisfied, that means that whatever U primes and V primes you will get, they will satisfy continuity. They may not be correct U primes and V primes to give you Un plus 1 and Vn plus 1. But they will satisfy continuity because of the fact that this equation number 4 is satisfied in an indirect form in terms of P prime. But whatever P prime you got was ultimately substituted in U prime and V prime to get your new velocities. Okay. So this constraint of equation number 4 being satisfied means that continuity is satisfied. Now to satisfy the continuity with this assumption, what happens is that the P prime terms in the second expression where we have neglected the neighborhood terms, they have to take the burden, so to say. If we had used the correct expression, we would have got the correct P primes to give Pn plus 1. But now that we have neglected something, to ensure that this U prime and V prime will have to satisfy continuity because equation number 4 is being satisfied, right? So P primes will have to take the burden. They will become more incorrect. They're like trying to overcompensate. Okay, so P primes will get values in such a way so that the U primes and V primes you get will have to satisfy continuity. But that should not have been the case because there were neighborhood terms in the second equation, second expression. So P prime terms become more incorrect than they should have been. So they take the burden to overcompensate and they become more incorrect. Well, more incorrect than what? More incorrect than what they should have been. But the velocities U primes and V primes we get, they are not that incorrect. Okay, because these P primes are trying to ensure that the U primes and V primes we get are going to satisfy continuity. So in a way, your U primes and V primes are not that incorrect as your P primes are. So here we are not quantifying how incorrect they are. We are just having a discussion about the fact that this method results in our p primes which are more incorrect than u primes and v primes are. U primes and v primes are less incorrect, or they are more closer to the correct values than p primes, because p primes had to overcompensate to ensure that our u primes and v primes satisfy equation number 4. So for this reason, what we do is, when we are updating the pressure value, so we had a step where we said that the new P star value is the old P star value plus P prime, right? So here what we do is we actually multiply it by a under relaxation factor alpha P, where this alpha P is typically around 0.8, because pressure had to overcompensate, so it may have p prime may have values which are uh, further away from what we want. So if we keep the complete p prime value, it may result in divergence. So we add a part of it, around 80% of that, so that we do not over exceed the converged value pn plus 1 towards the end. This is for the sole reason that your p primes were overburdened because of the assumption to ensure continuity, and they may have values much larger than what they should have.
So how do we get this value? How do we get this value?
Which value?
0.8.
That's through numerical experiments and through research papers. There is no analytical expression that you can use to derive the value. This is a lot of experience and numerical experimentation involved. And this is a typical value. I mean, a value larger or smaller than that will work in your problem. This is just a typical value I'm giving. You can use, you can have values which may result in quicker convergence. Is that clear? Now, since u prime and v prime, as I have written in the beginning of this page, are not that incorrect, so we don't under relax them. We just let them. Just write, we do not under relax u prime and v prime. Okay, so u prime will be equal to u star plus, new u star will be equal to u star plus u prime without any relaxation factor. So therefore I can say that computations in simple converge to our final un plus 1 and vn plus 1 in the time step via a series of u stars and v stars that satisfy continuity. That are the ones that were in the on the dashed line. And this is actually a quite a good feature of this algorithm, that these intermediate velocities which satisfy continuity are quite reasonable. Okay, in the sense that they are physically correct because they satisfy continuity. Continuity is mass conservation. Continuity being satisfied is actually quite an important condition. So that pretty much ends our discussion on simple. Well, just a couple of more things regarding under relaxation. So we had, if you remember the predictor equation, in the predictor equation we had u star and v star which were solved using an iterative method, right? So we had u star new equal to some expression where we had u star old, right? So when we get this u star new, we actually under relax it. So what we do is we say that u star new is equal to u star old plus some alpha times the difference between u star new and u star old. So we solve for the new values in one iteration, but we do not add or we do not use that u star new. We use a value which is somewhere between u star old and u star new. So this alpha typically is actually 0.5. And the reason for this is that the flux terms that we are using are at the previous time step. So we are using Fn. So there is some assumption, right? The flux terms are not at the same time step, or they're not f star values using this u star new values. Ideally, they should also be have the same velocities, but we neglected we used the flux at the previous time step for three reasons that we have discussed to make our life easier, linearize it, set up a direction for upwind, and to decouple the equations, right? So because of this assumption, we under relax it so that we may because our solution may go in the wrong direction if we use the complete value of u star. Every iteration is under relaxed. Okay. The Poisson equation, the pressure Poisson equation that we have is over relaxed. It's an elliptic equation, as we have discussed in the past for our heat conduction equations also. So P prime can be over relaxed to enhance the speed of convergence. So these are useful tips that you can put into use if you start implementing these things in the future. Because it may happen very well. I mean, these parameters can also controlled in commercial and open source codes. So usually you will press a button, but there are files or there are options where you can play around with these values. So it may happen that you are getting a divergence, and these are some checkpoints. So I usually what I do is I have a list of things written that typically can be done in the order of trying them. Okay, so this lecture could become the most useful lecture for you, in the sense that if your code is diverging and you are confused what to do, you could try these things and it may work. Okay. So one last discussion on implicit methods. Now, till now we talked about semi-implicit methods. But what about fully implicit methods, where our flux terms are also at n plus 1th time? If that is the case, then we get a more accurate result, right? So for that, there is not much of a change, except that in the algorithm we have to make a change at 2 or 3 points. So let's go to the algorithm, and then I'll just write the changes in the steps we need to make. So this is the algorithm. So in step number 2, we said find f n f. So here what we do is that we use, instead of fn, we use an f star. So we get another loop, which is called a nonlinear loop for mass flux. So to start with, yes, you start with fn. So let's talk about the how you work with it. So you start with an fn because you only have the previous time velocities, right? And then you you proceed further until we reach step number 6. So now we have updated u stars, v stars, and p stars, and now we are ready to continue. So earlier what we did was we went to step number 3. And in step number 3, the only difference is that now your u star, v star values are calculated using the new p star, because we have updated p star. But what was the flux, mass flux? That was still at fn. So now what we do is, instead of using fn, we use an f star. So mass flux is basically in terms of u star and v star values, right? I mean, in terms of velocities u and v. So in this semi-implicit method, mass flux always was at the nth time velocity. But now we have these intermediate u star and v star values that satisfy continuity. So we calculate the mass flux at this u star and v star which satisfy continuity. So we call it an f star. Okay. So what we are doing is we are using an updated or up-to-date value of the flux terms also. But they are just at the previous iteration, not at the previous time step. Okay. So when the iterations converge to un plus 1 and vn plus 1, then the flux will also converge to un fn plus 1. So ultimately your equations that you are going to solve are going to solve for with an fn plus 1. Except that you are still getting the benefit, those 3 benefits, in the sense that you are using flux at the previous iteration, so that they are available. You are solving for the velocities u stars and v stars, which are different from the velocities used for flux, because they are at the previous iteration, not the previous time step. That's the only difference. Okay. So in fact, we don't even need a separate loop for it, because that loop is the same loop as the loop for convergence of what did we call this loop? Convergence to n plus 1. This loop. In this loop, we keep updating the flux term. So instead of going to step number 3, as in step number 7 we have here, we go to step number 2 and update our flux as well. Pressure we don't touch. Pressure is p star, that is updated. And then finally in step number 8, when we write the updated values, we also update the value of fn plus 1. So just with this tweak, we are able to get a solution to fully implicit. So why? I mean, we don't use semi-implicit. We actually use fully implicit in many cases. It makes more sense. Right? Except that chances of things going wrong are much higher in fully implicit, because now we are changing the flux as well. So it can lead to divergence. But you will understand these things when you start working with CFD. All right. So it's a very standard technique. In fact, this is called using non-linear iterations So whenever we have something, let's say in this case we had a flux term times un plus 1. So it was non-linear because this flux term contained a un plus 1 as well. So that will result in squared. So we have iterations, and in iteration we use f star, and then we solve for, in this case we don't solve for un plus 1, but let's say we solve for u star. But this is from old, and this we are solving for a new value. So they're very close, just one iteration away. So they'll be close. And when the iterations converge, they'll have the same value. So that means you're solving for something which has the same velocities being used. So in step number 2, I'll say find f star f using latest u star velocity. And when I say u star, it means the one that satisfies continuity, not the one after predictor step. Because we reach this step only when we have continuity or divergence free u stars and v stars. Questions? That's it. So that's the end of simple and the fully implicit method. In fact, the simple, as you see in software, they will be fully implicit. So that's a bit confusing because semi-implicit, what we said semi-implicit meant was that we are using flux at the nth time. Everything is at the n plus 1. But Patankar, on the other hand, who developed this method, called semi-implicit, the word was given to the neglecting the neighborhood terms as making it semi-implicit. But these are just terms. As long as you understand the ideas, things will be okay. Okay. So in software and codes, you will see that semi-implicit will be using flux at the n plus 1th time. So you get confused. Why is it called semi-implicit? The semi-implicit is because of the neglecting the neighborhood terms, as Patankar coined. But that seems a bit incorrect in the sense of the use of the word semi-implicit, but that's okay. Are these ideas clear? Not the terms. Terms are okay. Okay. So for our discussion in this course, we will use the word semi-implicit for using the flux at the nth time, because that sort of goes well with our definition of semi-explicit as well. And then you'll see more methods like simpler, piso, and so on and so on. So the differences will be very minor between this and those methods that you see. So for example, there's something called a simple revise that Patankar proposed, and that is there in most of the codes. So the difference there is a minor one. So for example, here we saw that the pressure has to be under relaxed P prime because it had to take the burden, right? So what we do is, rather than using an update formula for pressure in the same way, we modify the update formula for pressure, so that in one step we can get correct values for pressure P primes as well. So they are very close to the actual pressure, because pressure is so far away that we have to do lots of iterations to reach that Pn plus 1. So if you could modify the method, we can reach that Pn plus 1 very quickly. So that's simpler. But again, most of the ideas are very similar, only one step changes. But the aim of this course is to get you comfortable with these methods, so that whenever you read a new method, you will easily make sense of it. So we have made you equipped to understand any advanced CFD concept from now on. Of course, I mean, these are rudimentary ideas. They are not used as such. A modified form will be used, but they will be easy to understand. Okay. Right, so that's the end of this. Now I also wanted to have a quick demo of an open and a finite element code. So I'll do it. I mean, that's not a part of syllabus as such. Otherwise, are there any questions before we do that?